So hello everyone, I'm Ionel. I'm a postdoc in Rice Lab working with Joey Gonzalez and Jon Stojka. And today I'm going to talk about ERDOS, which is a platform we are building for developing and testing self-driving cars. And this is joint work with a bunch of other people from the lab, including Sukrit, Peter, and Alvin. My talk is mostly focused on the systems challenges of building autonomous vehicles. And throughout my talk, I'm going to use this example software architecture of an autonomous vehicle. In an autonomous vehicle, you have a bunch of sensors, such as several cameras, LiDARs, and radars that send and generate data. And this data is sent to the first big component, which is perception. Perception is responsible with creating an understanding of the world and the environment. And it has components such as object detectors, traffic light detectors, traffic sign detectors, and as well, it's responsible to localize the car at decicentimeter level within the world. The information that is outputted from these perception components is sent to prediction, which builds a representation of the current world state, and it tries to predict the trajectories and the future states of the actors in the world. So in other words, it tries to predict how a car is going to negotiate a junction or if a pedestrian is going to cross the street or not. The outputs from the prediction and combined with the outputs from perceptions, they are sent to the planning component, which comprises of several modules. At a high level, there is route planning. You can think of it as almost like Google-style planning. It does planning at coarse-grained waypoints. Then this plan is refined by a local path planner that tries to minimize jerks to ensure that you don't collide with other cars and in general to offer a smooth ride experience. Finally, the outputs from the planning modules are sent to control, which actuates and sends commands to the car, such as braking, acceleration, and steering. In our work, we are tackling the interesting research challenges of building the system to run all these components, and we are interested in how to connect them and how to execute them. And this is very difficult because autonomous vehicles, they continuously interact with the environment, and the system must ensure that an action is taken from the moment the sensor data comes in up to at most 1 to 200 milliseconds. And this is required because the autonomous vehicle has to be faster than it takes a human to react in order for an autonomous vehicle to be able to claim that achieves at least as good safety as a human driver. The other thing is that autonomous driving is not a solved problem, and this has a bunch of repercussions. At the moment, there's a lot of rapid innovation that is happening in the space of autonomous driving. If you look at some of the challenges in autonomous driving, what you can see is that all the top 5 best car detector models are all from 2018, and they also run 4 to 16 times faster than the best detectors that existed back in 2015 and 2016. And this applies as well to pedestrian detectors, lane detectors, and so on. And the repercussions of this is that the system must ensure that and provide a way for users to run several models to do shadow testing and as well to deploy them quickly to test them on the roads and in an environment in which still the end-to-end deadlines are satisfied. To make matters worse, many of these components, they have variable runtime. So we've done an analysis of some of the components in a popular open source autonomous vehicle from one of the big internet companies, and we found the following. Initially, we zoomed in on the traffic light detector from this company, and we measured its runtime. And here I'm showing a CDF of a runtime for the traffic light detector, and lower is better. Now, it turns out that in this case, the runtime varies up to 3-4x, and it depends on the environment in which the car runs. This happens because the detector is a two-step detector. In the first phase, it selects regions of interest in which there may be traffic lights, and then it classifies the traffic lights to figure out the colors. And depending on how many traffic lights you have in a frame, the traffic light detector is going to take longer. Now, on an absolute scale, maybe you're going to think that 10 milliseconds is not that much. The problem is that as you compose these modules together, 5 milliseconds in the traffic light detector, 5 milliseconds in the object detector, in prediction, and so on, and quickly they add up. We've done the same analysis for prediction, but this time I'm showing the results on a timeline. So on the x-axis, we have time, and the y-axis, we have prediction runtime, and lower runtime is better. And what we found out is that prediction usually takes around 20 milliseconds, but then there are some big outliers, and in this instance, there is one instance when prediction took longer than 100 milliseconds. And that's enough to miss your end-to-end deadline. And what makes matters even worse is that things add up like compose. So we've measured across perception and prediction, and we measured, this is a CDF of inter-output time. So that's the time between outputs from the prediction component. And what we found out is that sometimes it takes up to like 900 milliseconds. There's up to 900 milliseconds when prediction is silent. And if you remember from the previous graph, actually the prediction runtime is somewhere in the 20 to 100 milliseconds at most. The reason why there's so much variability here is that upstream perception sometimes runs behind, and it internally decides to drop some frames, which has a knock-on effect on prediction and on the entire pipeline downstream. So the conclusion is that it's very difficult to guarantee end-to-end deadlines because there's all variability in runtime. The other thing is that there is some non-intuitive trade-offs, and depending on scenarios, in some cases it's better to run a fast but low accuracy model rather than a slow and a high accuracy model. So to exemplify this, let's imagine we have a hypothetical object detector that runs in this simulator, and it's great, and it detects the cars and the pedestrian and places bounding boxes on the frame. Now, maybe this detector takes an entire second to find these bounding boxes. The problem is that in that second, the world completely changed. And in the context of autonomous driving, you actually want an understanding of the world at this time. So if you look in the second image, what you can see is that the bounding box for the car actually does not even overlap with the car at all. So we've devised an experiment to show how aggressively accuracy decreases depending on the runtime of the detector. And the way we do it is using a simulator. We have ground-labeled data with perfect bounding boxes. So we take at time t, the frame with the bounding boxes, and we simulate a perfect object detector, and we effectively introduce a delay. In this case, the perfect object detector, we simulate that perfect object detector that takes 40 milliseconds. And then at the end, we compare the bounding boxes from 40 milliseconds ago to the current bounding boxes, and we compute the accuracy. So I'm going to show you the results. Like for the object detection, the results are like we are still waiting to get the latest plot, but I'm going to show you the results for segmentation. And in this plot, on the x-axis, I have runtime. We vary the runtime of the segmentation module. And then on the y-axis, we have the real-world accuracy metric for segmentation, and it's MIOU. So what we found is that the accuracy degrades quickly. So if you're familiar with segmentation, semantic segmentation, like the good models, they usually get around 90% accuracy, whereas in our case, even a runtime of 5 milliseconds is enough for the world to change more than that. So the conclusion is that both accuracy and runtime matter. And the last point I want to make is that in an autonomous vehicle, ideally we would set these end-to-end deadlines depending on the speed at which we are driving. So using the same semantic segmentation, we've done an experiment in which we vary the speed at which the vehicle is driving. On the x-axis, we have speed in meters per second, and we've set the runtime of the semantic segmentation to 20 milliseconds. And what we can see is that depending on the speed at which you're driving, your accuracy decreases in the same amount of time, and it decreases quite aggressively. So the point is that end-to-end deadlines, they should be dynamic and should adjust with the speed at which the vehicle is driving. At high speeds, you need tighter deadlines. And to make matters worse, in terms of system challenges, there's other traditional data system challenges, such as the system must provide high throughput with low latency. It must offer fast recovery from both software and hardware failures. And it must provide deterministic logging and replay so that developers can investigate scenarios that were challenging or when bad things happened. And last but not least, the system must provide security. So this is where ERDOS comes into the picture. We are building Elastic Robot Data Flow Operating System, and we are mainly building it to target to do the research in this area to see how we can tackle these challenges and how to solve them. In ERDOS, applications are developed as a data flow graph of operators, and the operators can register callbacks, receive data, process data, and send outputs. So in this example, every single module becomes an ERDOS operator. The data between operators is sent on named typed data streams. And these streams can have associated, can have labels associated to them, which you can think of them as being properties. One thing that I want to point out that every single message in the system is logically timestamped, which means that, like, depending on the application you're developing or your needs, that logical timestamp can be the camera frame generation time, or it can be a sequence number, or it can be the wall clock time. So let's now switch a little bit into like a brief look of how the API, how our ERDOS API looks like. So I'm gonna walk you quickly through an implementation of an object detector using our Python API. We also have a Rust API, and hopefully not too far in the distant future, we are gonna have a C++ API. So in ERDOS, developers must implement a class in order to define an operator, and in the init method, they can initialize the state for the class. In this case, they create a TensorFlow session. Then they also have to provide a setUpstream method, which is used for establishing the connections between the operators. This setUpstream method receives a bunch of input streams, and then the developers can decide on what input streams they want to register callbacks. In this case, they care about the camera stream, so they filter out all the streams that are of type camera RGB. The last thing that is specified in the setUpstream is the output streams from the operator. In this case, because it's a detector, it outputs a stream of type bounding boxes. And finally, the developers have to implement the callbacks. In this case, the on-frame callback is invoked for every single message, and in our case, the frame. When it runs the TensorFlow session, it runs the inference, gets the bounding boxes, which it sends them out on the output stream. Now, in a pipeline, you have several ERDOS operators that need to be connected, and we do that in a driver script. In this example, I have a camera operator, which interacts with, it effectively implements the driver to communicate with the camera, then an object detector and object tracker. I first add the operators to the data flow graph, and then I connect the operators. I connect the camera operator to the detector and the tracker, and then the detector to the tracker. I don't have time to talk about these things, but I'm just going to briefly mention, and if you want to hear more about them, do find me afterwards and we can talk. There's some nice features that we have in ERDOS. So one of them is that our operators are multi-threaded, and we've managed to achieve multi-threading without requiring you to manually lock when you're coding by being careful of what API we provide. And we make heavy use of punctuations for progress tracking, for enabling deterministic execution, and as well, punctuations help us with fault tolerance. And the last important feature is that in our case, the operator state is automatically partitioned by time, so then you can do things like I care about the last 10 seconds, the bounding boxes from the last 10 seconds, so that I can use them for tracking. So I want to quickly switch gears into an upcoming feature that we are currently developing and that I'm really excited about. And this feature has to do with the end-to-end deadlines. And the question is, how do you divide an end-to-end deadline to per operator deadlines? And the way it works in ERDOS is that users have to define an accuracy function per operator, and this is a function of deadline, input staleness, and input accuracy, and it's an indication of the accuracy that the operator can achieve within that deadline. And ERDOS uses these functions to basically assign time and divide the end-to-end time into per operator deadline. One nice thing is that ERDOS can do these things dynamically. So if you, let's say if your object detector has assigned a deadline that it doesn't meet, so it misses, then ERDOS can dynamically take time off from the planning or prediction, or it can decide to completely skip planning or skip prediction. Now, ideally, this problem wouldn't happen if we have anytime operators. So an anytime operator or an anytime algorithm is an algorithm that returns a solution at any point, like if it's interrupted. And the more time it has, the better the accuracy it obtains. But in practice, the problem is that there's not that many anytime operators. Planning is one of them that you can do anytime. But for things like object detection, at the moment what we have, it's not anytime. It's more like I run a model, and then when the model finishes, the accuracy jumps and spikes and goes up, and it's basically a step function. Now, if you translate actually this accuracy into real-world accuracy, and we change our operator to be something slightly nicer, in which you return the old bounding boxes if you don't have enough time to finish running inference, then that's how the real-world accuracy are going to look. It's going to degrade with the environment changing, and then it spikes up when inference completes, and then it starts degrading again. But in ERDOS, because we expose these deadlines into the callbacks, what you can do is you can run models in parallel, or you can make decisions that, like in this instance, because I don't have that much time, it actually makes sense for me to run this faster, lower accuracy model rather than the slow model with high accuracy. And what that means is that we can offer poor man's anytime, and you can have both models, and you can benefit from both models. So if you have more time available, then you can get higher accuracy. So in the last part of my talk, I'm going to switch gears into Pilot. So Pilot is a simulated self-driving car that we are building on top of ERDOS. And our goals, our reasons, there's twofold. On one hand, with Pilot, we are driving our systems research and innovation. But then we also want to offer Pilot as a platform for people to evaluate and test their machine learning modules. It's a plug-and-play architecture. If you are, for example, let's say, working on object tracking, you can bring in your object tracker in our pipeline, and you can test it to see how it works with the other components, how it interacts, how the uncertainty propagates from a component to another. The other thing I want to mention is that ERDOS runs on top of the Carla open source simulator. So in terms of ERDOS, it's currently under heavy development. We have, for several components, we have many options. So for object detection, we have five models. We have a model for lane detection, which is we are currently improving. We are working on prediction, but we have solutions for path planning. And we are doing all this work in the context of the Carla Challenge, because the Carla Challenge provides us with a set of challenging scenarios to test our application. And in Carla Challenge, there is several tracks. And depending on what part of research you're running, you can test it in a different track. So let's say if you want to test mostly your perception, then you're going to target track 3, because there in that track you have access to LiDARs, HD maps, GPS, and cameras. So you have access to the entire suite of sensors. But then if you are more ambitious, you can go for track 2, where you can run in camera-only mode. So in this video, I'm going to show you our pilot running the Carla challenge. Let me see if this starts. So the top left image is basically our object detector. Bottom left is our traffic light detector. On the top right is top-down view of the world. And bottom left is semantic segmentation. And in the Carla challenge, there's a bunch of scenarios that you have to successfully negotiate. What we'll see soon is that I think in this scenario, there is a vending machine that appears. And then there is a pedestrian that jumps in front of the car from behind the vending machine, and the car has to make sure that it completely stops and doesn't hit the pedestrian, and then it carries on driving. So, and there's many scenarios like this that are defined in the challenge, and you have to successfully negotiate them. One thing that I want to mention is that the nice thing is, because we are running in simulation at the moment, in pilot, we are currently providing perfect versions of many of the components. So you can initially test your component using perfect data. And then as you feel comfortable with the component, you can plug in, take out and plug in our components. And then you have to deal a lot with the uncertainty and see how your component integrates in the entire system and how it affects the end-to-end driving experience. So in this video, I'm showing it's an old demo, but what I'm showing here is that you can run several detectors in parallel. The bottom part of the screen, so the left-hand detector, it's not as noisy as the right hand, but then it's not as good as the other detector in detecting pedestrians that are far away. And at in the top two windows, you can see the model, the semantic segmentation model that we currently have, and you can completely compare that with the ground truth semantic segmentation. So to conclude, we are developing a stateful data flow system that is designed for enabling research in the space of autonomous vehicle. As well, this comes with Pilot, which is our self-driving application that enables researchers and machine learning practitioners to test their models and algorithms. Both projects are available and are open source and are available at that address. Thank you, and I'm happy to take questions. Yes. So many of ERDOS is on the system side. Many of the open source projects, they are developed on top of Rust, the robot operating system, which is effectively a publisher-subscriber middleware. It has a super nice environment, and it's nice with Rust that you can plug in components. You can bring in a new Rust node, and you can subscribe onto a topic. But the problem is that it was developed mainly for robots. So it provides you high throughput, but then if you want to write a Rust node, you have to manually deal with concurrency, lock your state and share your state or call callbacks. So that's kind of going to hinder a little bit rapid innovation. And then it does not have any resource management. It doesn't do end-to-end deadlines. And it has no fault tolerance. So its master is actually a single point of failure. And then if you want to make your Rust node fault tolerance, there's no solution at the moment. You have to use an external system. And at that point, you end up building your own resource manager, and you're building up ERDOS. And some companies, they started migrating from Rust, Apollo. They are doing a new system, but I think it's still heavily influenced by the architecture, by the Rust architecture. And whereas here, we are pushing for a different architecture. Any more questions? Okay, you can find me at the back if you have more questions, and I'm happy to talk with everyone. Thank you.